All right, so page 11, we saw a new graph. And at first it didn't have anything on the y-axis because the first two questions have you view it and do the problems as an acceleration time graph. And then here in just a minute, the bottom two questions are going to treat it as a velocity time graph. Okay. And so you really need to get in the habit, if there's a graph, read the axes. Okay, because when you, step one, read a graph, you need to know what you're reading. And then whenever you do slope or area of a graph, what's on the y-axis greatly changes depending on what is plotted. And so last time we took a look at the acceleration graph, how you can read it and how it relates to the pull. Remember, acceleration happens because of a force. And so if there's a negative acceleration, somebody was pulling you or pushing you in the negative direction. Maybe left, that's fine, doesn't have to be, but the negative. And then that constant pull in the 2 to 3 second mark started decreasing, okay? And we said that because you originally were going in the negative direction and someone pulled you in the negative direction, there was a speed up, right? First 2 seconds. And that's quite a bit of speed up if you look at the shape of that rectangle, right? Look at area, because area gives us a change in velocity when it's an acceleration time graph. And then 2 to 3 seconds, you still have a negative acceleration. We're still speeding up, but now it's just a little bit. If you look at the area of that little triangle, it's basically 1/4 the size of that blue rectangle, yes? So for the first 3 seconds, we're still speeding up in the negative direction. And then what happens 3 to 4 seconds? We're not speeding up in the positive. You can't go speed up, speed up. You got to slow down when the opposite direction pulls on you, right? And so we slow down a little. In that green and green symmetry, if you recognize the symmetry, you know that those two changes in velocity, they cancel each other out. And so you could save yourself some math time by you don't need to calculate the area of either of those triangles. Now it's not going to hurt you, base times height divided by 2, but you don't have to if you recognize symmetry. And then we made our way to 4 to 6, that next blue rectangle, and hopefully you saw more symmetry, right? And I'm guessing, since I don't have anything written there, that's where we need to pick up. And so 4 to 6 seconds, what's happening? It's the opposite area, right? Equal in magnitude, opposite in direction to the 0 to 2. And so if those cancel, what's the velocity? Not that this is a velocity graph, but what's the velocity at that 6 seconds? Not the opposite of 2 seconds, but you're returning to whatever, it kind of bookends, okay? Not automatically 0, but what was the velocity when the timer began? Right, so at 0 seconds, it was -3. We sped up a lot, we sped up a little in the negative direction, and then we slowed down a little, and we slowed down a lot. At the end of the symmetry, we return to -3 meters per second, okay? How? Let's do some math, okay? Base times height me. In the first 2 seconds, we have a negative area, a negative change in velocity, so that -3 gonna become more negative. Well, it's 2 seconds by -3, so it's an area of -6. And so when we put that with our original -3, at the end of 2 seconds, our velocity is -9. So I'm just taking it segment by segment. So she wanted to know how we get at the end of 6 as -3. So I said, well, let's do the math behind it. So we're going to progress the velocities at the end of each segment. And so if you start out at -3 and you have a -6 change, final minus initial, okay, you should get a final velocity of -9 meters per second. Then we come to that little triangle. We said we're going to speed up a little bit, right? And so it's a base times height divided by 2, 1 times -3, half that. What's the area of 2 to 3 seconds? -1.5. And again, that -9 is going to become more negative because it has a negative change. And so at the end of 3 seconds, our velocity is -10.5. And then we come to 3 to 4, where we have a positive 1.5. Now I have a change in the positive direction. So our -10.5 is going to become more positive by 1.5. So it would be -9. Notice the -9s bookend the green symmetry. Keep it going. 4 to 6 seconds. We got that 2 by 3, but now it's positive. So our change in velocity is a +6. And so that -9 needs to become more positive. What's the final velocity at 6 seconds? -3. And so it bookends your symmetry, okay? Now you wouldn't have to do that math, maybe next time, if you recognize that when you have the symmetry, that speeding up and slowing down cancels each other out and you return to whatever you started the symmetry with, okay? Does that help? So at 2 seconds, we were -9.
Yes.
And you get where that came from? And then 2 to 3 seconds, we had this small triangle. So base times height divided by 2. So a base of 1, height of -3, and then half of -3, -1.5. So that -9, you start 2 seconds. Yeah,
Okay.
yeah. That -9 has to become more negative because you had a negative change.
Then add a -6, then add a -1.5,
Yes.
and then subtract it.
When it starts slowing down the other way, yes, then it would, there we go.
Got it.
And all this is good because the question we didn't answer last time, number 1, does the object ever change direction? If so, when? Have we changed direction so far, 0 to 6?
Yes. Yeah. Because
The pole has changed direction, but has our object ever had a sign change for its velocity?
No.
No, it's always had a negative velocity. So to answer the question, you need to, we want a sign change of your velocity. The sign change of acceleration just means your pole is changing, okay? If it was a position graph, a sign change would mean you're on the other side of the origin, whatever that's deemed to be, okay? Always read your axis. And so from 0 to 6 seconds, we are just going in the negative direction. All of the velocities we've seen have all been negative, negative, negative. But we are becoming more positive, right? That -10.5, the -9, the -3. Let's do another increment. And so 6 to 7 seconds, that change in velocity, it's a single square, if you will, a 1 by 3. We get a +3 change in that 6 to 7 area. So if we started 6 seconds at -3 meters per second, and then we're slowed down by +3, what's our final velocity at 7 seconds? We are at 0. So at 7 seconds, we've now slowed down to 0. Is that automatically a direction change? No, we've been going in the negative. Now we came to a stop. Maybe it's a drive-through situation, right? You got to look at the future. What's the future? 7 to 10 seconds. Who's pulling on you? The positive. And if we're at a stop at this point and the positive pulls on me, what am I going to do 7 to 10 seconds? I'm going to move in the positive direction. And even though the acceleration magnitude is decreasing, it's still going to speed me up in the positive direction. And so going down 6 to 7 seconds, we were still going in the negative direction. At 7 seconds, we came to a stop. And then after 7 seconds, we were moving in the positive. And so to answer their question, if so, at what time does the change occur? How would we answer this? What time does it change direction?
Between 7 and 10 seconds.
Well, it's at 7. That's when it begins going in the positive, at 7 seconds. Okay, so that change direction, it's not always about the stop. I know that a lot of our examples, it turns into be, but watch out, there could be a drive-through example, right? And so it's about the past direction, the current stop, and the future direction. Good deal? So we used a lot of area there. Again, area is a change in velocity. You got to know something about that initial. If you don't know an initial or final at any point, you really can't answer the question. You just know about the changes in velocity, okay? And it looks like we already did number 2. We did that in the symmetry. And so we found that total area. Say again? Yes. There we go. And so we found the areas that didn't cancel, basically, right? So about 10 seconds, that was the whole entire graph. And so you recognize the first 6 cancel out, positive, negative area. And so really you just have to find the area from 6 to 10. So that little rectangle square, and then that triangle. Put them together. That's your area for the whole thing. And notice we had to include the initial velocity given or at 6 seconds, it returns to that. So I could have also said 6 to 10. And we get our final answer, positive 4.5 meters per second. Good on number 2. Okay. So here in a second, we're going to switch to questions 3 and 4. And what's different about those, and hopefully it goes quicker. Okay, students are usually more comfortable with position and velocity graphs than they are acceleration. But they say now the axis is a velocity time graph. Okay. And so let's kind of recap. What do we remember about velocity time graphs? So you can read it. If you do the slope of a velocity time graph, what does that tell you? Acceleration. So the change in direction on a velocity graph, you would just read the velocities, their signs. And so the slope, though, you rise, change in velocity over change in time run, that's acceleration. And then if you do the area of a VT graph, what does that give you? Displacement, which is defined as change in position. There's that delta symbol again, y'all. Anytime you do area, you've got change, delta, okay, something. And so now it says the object is at position positive 4 meters at 4 seconds. So that's an instantaneous position, right? 3, what would be the acceleration at 3 seconds? So kind of like an instantaneous acceleration. Well, we just said we got to do the slope But you don't want to do the slope from beginning to end, just at that 3-second part. Now, I know my graph is cluttered as an acceleration graph, but try to, think of it as a velocity graph. And so at 3 seconds, oh, it has a velocity 0. Does that mean you have acceleration 0? That's a common misconception, okay? It has a momentary velocity of 0, but the acceleration is slope. Is there a slope at the 3-second mark? Yes, and so that green diagonal there is going to be the line we need the slope of, okay? So we want the slope of that second segment. So 2 to 4 seconds. Or you can use any time intervals of that, right? I'm going to do 2 to 4. If you do 2 to 3 or 3 to 4, that's fine. We should get the same answer, okay? And so slope is that rise, change in velocity, over run, and each of those are final minus initial. Timing, if I say I'm using 2 and 4, I need to make sure I grab those velocities, and it would be 4 minus 2 with final minus initial. And so I go back up to get those 2 velocities. Don't mix them up, y'all. Final minus initial matters. So at 4 seconds, I have a final velocity of positive 3. And at 2 seconds, I have negative 3. And so I'm going to say 3 minus a negative 3, which turns into plus, right? And so we get a positive 6 over 2, or a positive 3 meters per second. And the unit for acceleration? Squared. Or if you look, if I included units in my calculation, meters per second is acceptable, okay? And then number 4. Number 4 says, what is the initial position? They're meaning the very initial, so at t equals 0 is implied there. So position, you can't get position directly from a velocity time graph, but I can get displacement. We said do the area, that gives you displacement. Who remembers the defining equation for displacement? Right, final position minus initial position. And so 0 seconds is mentioned, so I'm going to call that the initial. And then if you go back up to that prompt, they give you 4-second position, which also happens to be positive 4. So I'm going to say 4 is our final position. So I need the area 0 to 4. It has to coincide. Now, luckily for us, we've already done the math behind this, because the magnitude of the area we found earlier is the same. It's just not going to be the same physics. Now it's going to be displacement. So I'm going to scroll back up. 0 to 4 has a blue square and 2 green triangles. What do we know about the 2 green triangles? They cancel out the symmetry. Do I need to bother? No, okay. Now don't use the -3, -9 stuff. That was based on the velocity given for prompt 1. But I do recognize, hopefully, that, if we were to cut what we're looking at the 4-second mark, all I really need to do is the area of that first blue rectangle. It's a 2 by -3. And so we come down here. And I'm just going to state that we recognize that the area or displacement from 2 to 3 is going to cancel the area or displacement 3 to 4. And so really, it's just the displacement of 0 to 2 that equals the displacement 0 to 4. Not that you have to write that, but this is kind of a teaching. If anyone ever goes back to look at it, why did she not do the area of the green triangles? I'm just giving a little clue. And so area, base times height, It was a base of 2 seconds and a height of -3. And I'm including units for fun there, just so we can see it every once in a while. Seconds in the numerator, seconds in the denominator. What happens? It cancels. And so we get a change in position of -6 meters, but that's not my final answer. They want the actual position that you started at. And so go to the defining equation. We know that the final position at 4 seconds, that was told to us, they said it was 4 meters. So that was given. And we are solving for initial position. So whatever, math order you do to solve this, or you can think 4 minus what number equals -6? 10, a positive 10, right? And so your final answer is positive 10. You start at positive 10. In the first 2 and in the first 4 seconds, you have a displacement of -6. So at 6 seconds, you end at the 4 meter mark. Good deal? So hopefully, velocity graphs feel a little better. I don't know. It could all still be, foreign to you. Practice makes better. I don't like the perfect, right? Nobody's perfect. No, nothing's perfect. So I tell my own kids, practice makes better. Okay, moving on to page 12. Bless you. I'm actually going to have y'all work on this, a small group. I'm going to give you and we'll set it up together, but this one, you may think, oh, I just got to look at it and it's a real quick answer. There's some thought processing going on here, okay? They give you position graphs and then they ask about acceleration. You can't just look at a position graph and immediately know acceleration. You got to do some thought process, okay? And so I'm going to give you about, 8-ish minutes to a small group this, and then I'll put the key up. It's also on Canvas if you don't want to wait on me. The key is on Canvas, but try it first. Always try it first, okay? It's okay to get answers wrong as long as we learn from them, right? Sure. Hey, make your mistakes today. That way you don't make them on the exam next class, right? Make your mistakes on a daily basis. All right.